Significant figures, the solution to the problem of measurement. So one of the problems with the way significant figures are typically taught is that you are taught how to determine the number of sig figs when you're given a number, okay, how many sig figs are there, and you're also taught how to add and subtract. It doesn't really tell you what sig figs are, or why we use them, or what they're good for. So first of all, before we can really delve into sig figs, we have to understand what measurement is. So, can somebody count how bright these lights are?
Yeah.
Can you count how bright the lights are?
It's like maybe 20 or 30.
Count how blue your jacket is. See, these are things you can't really count, right? It's just not natural to us. So it's like they were not easily quantifiable. But what we don't realize is that thousands of years ago, if somebody said, "Count how long something is," how do you count how long? I can tell something is longer than something else, but I don't know how to count how long it is, right? So we came up with some different measurements. Like if you, if any of you read the Bible or even the Quran, if you might have heard of a unit called cubit. Cubit is the difference between from your elbow to your fingertips. Only one problem with that. If I have a cubit, elbow to my fingertips, let's compare cubits. If I'm selling you stuff and she's selling you stuff and we're charging the same price, who do you want to buy it from? Yeah, because you're going to get more for your money, right? So, essentially, that is the problem with measurement. So measurement, we measure things that we can't count. But to measure something, we need to measure it against some sort of a standard, either a cubit or a foot or a meter or something like that. You know, the foot originally came from the king's foot, the length of the king's foot. Only problem is, every time you got a new king, you got a new foot, right? So foot is a little bit more universal of a standard, but we needed something a little bit more consistent. Now, for the longest time, the meter was just this platinum iridium bar that was in a museum in Paris, and everybody's like, okay, so this is our meter. This is arbitrary length. This is going to be our meter, and then everybody else is going to be based on this meter. To this day, a kilogram is still based off of a particular weight that's kept in a museum under lock and key in Paris. All kilograms in the world are based on this random weight. There's no rhyme or reason for why they chose that specific weight. We're working on a way to make it a little bit more scientific. Now the meter is defined as the fraction of the speed of light. But the point is, measurement is not perfect. When we measure things, we're measuring it against some sort of a standard, like a cup, measuring cup, or a tablespoon, or whatever. And that standard may not be perfect. So when we measure things, there's always going to be a little bit of error. There's always going to be a little bit of uncertainty.
Please wait, I want to sign.
I'm sorry?
I want to take a picture.
It is on the PowerPoint.
What?
It is in the PowerPoint.
It's on what?
PowerPoint.
So, a measurement can never be perfect because you're comparing it to a standard. And as hard as we try, standards are not going to be exactly alike, down to the last atom, right? I can't measure something down to the last atom as far as length, or volume, or temperature, or brightness. So all measurement is a little bit arbitrary. It's a way of quantifying something, and not arbitrary in a certain sense, because there is a standard by which we measure, but it's something that we made up, something we try to quantify that's not easily quantifiable. Turn into a number something, so that way we can compare different amounts. So there are different kinds of numbers. As I mentioned, there's exact numbers and there's measured numbers. Now exact numbers are numbers that can be counted. There's no uncertainty. So for example, the number of people in this classroom is an exact number. There are 6 people in this classroom, right? It's not 6.5, it's not 6.2. You can't have a half of a person, right? Even if you cut somebody in half, that's not a half of a person. That's just messed up, okay? Or if somebody loses a limb, there's still a whole person even if they're missing an arm, right? So you can't have half of a person. You can't have half of a table. You can have a broken table, but you can't have half of a table or half of a chair. So those things that we can count, those are exact numbers. Now, things that we have to measure, they're going to have a little bit of uncertainty to them. And that's where significant figures comes in. Now, as it notes here, when we use our calculators, we must determine the correct answer, but calculators treat everything as if they're exact numbers. So it just spits out how many ever decimals it can, because it doesn't know how to distinguish between something that has error or uncertainty and something that is in fact exact. So we have to do a little comparison on that. So exact numbers have no uncertainty, perfectly certain, and measured numbers have an uncertain digit. They have uncertainty or error. Okay. Let me know if I'm going a little too fast. Okay. Now, so there are 2 ways to have an exact number. I already mentioned counting, but you can also have an exact number if you have a definition. Like for example, 1 foot equals 12 inches, right? That's exact. Even though we measure things in feet and measure things in inches, the relationship that 1 foot equals 12 inches is by definition an exact number. Just like 100 centimeters is equal to 1 meter. By definition, that is exactly what a meter is, 100 centimeters. So there's no uncertainty there. So you'll notice a lot of times when you do conversions, and use conversion factors, it's not going to change the significant figures of what you start with, because the conversion is oftentimes a definition relationship, and therefore it has unlimited significant figures. Exact numbers are considered to have unlimited accuracy or unlimited significant figures. Okay. So let's take a look at some examples.
Sorry, can you go back a little?
Sure. Now I do have this this PowerPoint up on the website. You can feel free to download it and use it at your leisure. Just to let you know, it might be a little easier than taking pictures.
Oh.
Alright. So let's classify each of these as exact or measured. 1 yard equals 3 feet. Is that exact or is it a measured number?
Is it exact?
It's exact, a definition. The diameter of a red blood cell is 6 times 10 to the negative 4 centimeters.
This is measured.
That's measured. That's measured. You have to measure the diameter of a blood cell. You have to compare it to a standard. There are 6 hats on a shelf.
Exact.
Exact. Gold melts at 1064 degrees Celsius.
Exact.
Measured.
Oh, measure, yeah.
Yeah. You have to measure the temperature. Alright, cool. So now, what are significant figures? Now that we have an idea of what measurements are and exact versus measured numbers, what are significant figures? Well, significant figures properly understood refers to the actual act of measuring. So, if you're actually measuring, significant figures means that you measure all digits that are known with certainty plus 1 estimated digit. All digits that are known with certainty plus 1 estimated digit. So, this last significant figure of any measured number, that is uncertain. It's estimated. It could be a little bit more or a little bit less than what you would expect it to be. We'll go into that a little bit more in a second. Essentially, when we estimate, we're estimating between the smallest markings on our measuring instrument, whatever that happens to be. Graduated cylinder, ruler, thermometer, whatever. And another interesting thing about significant figures, it reflects precision, the precision of a measurement. All right, so measuring with significant figures. So let's take a look at this example. So you see here that we have the water level here in the graduated cylinder. Now when we measure water level of a graduated cylinder,
Sorry, Mike. Is it a rule that we can close the door?
oh sure, absolutely, thank you. Yeah. When we measure the water level of a graduated cylinder, you'll notice that the water kind of dips down a little bit in the middle. That dip is called the meniscus. And you always measure essentially from the middle of a graduated cylinder. So essentially from the bottom of the meniscus, if it dips down like that. Measure from the very center, at the bottom of the dip. Okay? So I can see that the bottom of this dip, well first of all, let me look at our numbers here. This is 15 and this is 20, and there are 5 markings in between them, right?
So which means that everything is tens? No.
So each
Ones.
marking is worth how much?
Ones.
1. Each marking is worth 1. So this is 16 then, this is 17, and this is 18. So I can be absolutely 100% certain that this is in between 17 and 18, right? It's less than 18 but greater than 17. You all agree? Okay. But I don't know exactly how far between this is. I have to estimate between these smallest markings. Now if you're going to estimate, what would you say this is? If I imaginary, in my mind, if I imagine 10 equal markings between these two spaces, roughly where would this be? Would this be 6 spaces up?
16.8.
17.
So you say 17.8.
0.5.
What do you say?
17.8.
17.5.
17.5? How about you? 17.5? 0.5? 0.6? It's very close to half, so 17.5 is very reasonable. But it does look like it could be a little bit above, so 17.6 is not bad either. I'd actually tend to lean more towards 17.6, but 17.5 is a perfectly good estimate. Notice that all of our answers are just a little bit different. It's because it's estimated. We can't know exactly where it is. I can't say definitively that 17.5 is better or worse than 17.6, because I don't have any markings to go by, right? I'm just estimating.
So can we do 17.5 something?
No.
Just round it up to
We can only
17.6.
estimate one digit. Because there's no markings in between here, I can't say it's 17.5 something. I can only estimate one digit between the smallest markings. The smallest markings are in the ones place, so I can only estimate to the tenths place. So, in that case, I would say this is probably about 17.6. So that always, so I know that it's between 10 and 20, and then I know it's in between 16 and 17. So the ones place is certain, or the tens place is certain. The 7 is certain. The one that's uncertain is the tens place, and I have to estimate that. But that's the last digit that I can estimate. I can't go any farther. Yes?
So with this ruler, like, so how we going to count?
Okay, so for a ruler like this,
Measure $1, so I don't know.
well, so if you have a ruler like this, notice all these little tiny markings, the millimeters. You want to estimate between those smallest markings. Now that's really tough because they're really tiny. But when you measure with appropriate significant figures, you always estimate between the smallest markings.
So now that I'm measuring $1 also.
We'll look into doing some examples of measuring in just a little bit,
Okay.
but you'll get a better idea of what I'm talking about. All right, let's look at some other examples. So, now before we go any further, I do want to talk about how you measure volume, because measuring volume is one of the trickier measurements to do, and largely it's because of these things called menisci, or meniscus. The meniscus for water tends to dip down like this, but if you have like mercury in a thermometer or something like that, it'll have a convex meniscus. In other words, it'll curve upwards. you always measure from the center of the tube. From the center of the tube, where the level is. So in a convex meniscus, like mercury in a thermometer, you measure from the top of the meniscus, from the middle of the thermometer. For a concave meniscus, where it dips down like water, you measure from the middle of the tube, likewise, but that's going to be the bottom of this type of meniscus. Does that make sense?
With this one, for the converse, you measure from the top. Then from the concave, you measure from the
Bottom, exactly. Now, if it's easier for you to remember it like this, you could also just say, I need to measure it from the middle. Wherever the middle is, that's where I measure it from. Does that make sense?
Mhm.
All right. Also, glass and water does funny things to your eyes. If you look at it from a particular direction, it looks like it's less, and if you look at it from a particular direction here, it looks like it's more. So, you got to be careful that when you're reading these, you have to read them at eye level. You want where you're measuring, the bottom of the meniscus, usually for water, you want that to be at eye level. Okay? Otherwise, the glass and the refraction will cause a distortion referred to as parallax errors. And you might actually get a quiz question in your lab about parallax errors, but parallax errors are essentially errors that result from reading volume measurements too low or too high, and it ends up distorting what the value is. Okay, so let's do some practice. Measure A and B, these two, to the best of your ability. I made these obnoxiously large so that you can see them from a distance. But estimate what you think this measurement should be in each case.
Is it at the top? You can see at the top.
Well, remember, these dip down, don't they? This is water. You see that downward dip?
Yeah.
If it's a downward dip, remember, you
So
always
50
measure from
bottom.
the bottom. Always measure from the bottom.
So is it 59?
Write down what you think the answer is. We'll go over it together in a second. Don't try to get me to get the answer before it's time. All right, you got the measurements? Best you can? All right, let's take a look. So for this one, the smallest markings are worth how much? 1.
Once.
So that means we can estimate to the 10th place. This is clearly between 52 and 53, right?
Yes.
That bottom? Clearly between 52 and 53. So you should have gotten 52 point something, right? So what would you say, 52.9? 9's a little high. I don't think it's quite up to 9.
7.
52.7 is a good guess. That would be reasonable. If you said 52.8, also pretty reasonable. 52.9 is a little too off, but it's not horrible, but it's not as accurate as a measurement as you'd like. I think 52.7 or 52.8 are probably the best. You could say 52.6, but once again, that would probably be a little bit off. And the more you practice with measurement, the more you'll get better at estimating those in-between values. Because when you're just starting, it's a little bit tricky. How many of you got 52.67, or 52.6, 52.7, 52.8, or 52.9? Good. That's good. Very good. All right. Now, what did you get for this one?
6.32.
6.72?
No, 32.
02.
No,
32.
6.32.
32. Okay. 6.32. Sorry, my bad.
Oh.
Anybody get anything different? Nobody wants to volunteer any others? 6.6. Anybody else?
The same. The same.
6.6?
I'm lost.
You lost? Okay. This is more accurate to the actual value, but this one represents the correct number of sig figs. And this is a little bit tricky. So, you did a great job of recognizing that there are 5 markings between 6 and what would be 7, right? Because this is 8, so that means there's 2 in between 8 and 6, but there's 10 markings, so each of those markings is worth 0.2, not 0.1. So this would be 6.2, 6.4, 6.6. Okay. Now, you have to estimate between the smallest markings. So 6.6 doesn't give you the same level of accuracy that you need. So 6.6 what? It looks like it's just a little bit above 6.6, doesn't it?
Yeah, 6.2.
So if you said 6.61 or 6.62 or 6.63 or 6.64, all of those would have been within the realm of possibility. It's a little bit trickier to estimate because between these two there's 0.2. So that's actually 20 markings you have to imagine between these two, and that can be a little bit tricky. But you can see it's just a little bit above that line. And so a 6.62 would actually be just about perfect. I would say 6.62, but you could really have 6.64 and 6.61, and those would also be reasonable estimates.
So sorry. So we are starting our measurement looking at that the black thing or the...
You look at the very bottom of the dip, the very bottom of the meniscus right in the middle.
Mm-hmm.
That's where you measure it. And then you have to estimate between the smallest markings. Since the smallest markings are 0.2, that's in the tenths place, you can estimate to the hundredths place.
So
You can
that's what I'm saying. This is one question in the test. He said that what is the estimated digit for the first picture and the second picture? For first picture, the estimated digit is 1.
Well, no, the estimated digit in the first one, remember we wrote, the answer was 52.7 roughly, right?
Yeah.
The estimated digit is
Tenths.
in the tenths place.
Tenths.
You estimate between the smallest markings. The smallest markings are the ones.
So it's 10.
So the tenths
And
place
how
is
we
the
can
estimate.
write it? How we can write it? You can write 0.1.
Yes, so like for example, if you were trying to indicate the level of uncertainty or error in the measurement, you'd write plus or minus 0.1 or a tenth for picture A. For picture B, you'd say plus or minus 0.01. So this one,
Yeah,
because your
100.
estimated digits in the hundredths place,
100.
would be plus or minus 0.01. Does that make sense? Your last significant figure, your estimated digit, you assume it has some uncertainty. Now you never actually really have to write out these error notes, like the plus or minus part, but it is useful to know that there is uncertainty in that last digit. Does that make sense? Okay. Let's take a look at a couple others. What about this length? Now, this is a really big blown up ruler, and you can see that the measurement it has over here is centimeters, right? So since this is centimeters, that means that the smaller markings are how much?
1 millimeters.
Well, they're millimeters, but in terms of centimeters, how much of a centimeter is one of these markings?
Tenth.
The tenths place.
Tenths.
1/10 of a centimeter, right?
Yes.
And since the smallest markings are in the tenth of a centimeter, that means I can estimate it to what?
Estimated
To the hundredths place. I have to estimate between the smallest markings. 1 digit past the smallest markings. So if I look at this, I clearly see that this line is between 1.1, 2, 3, 4, 5, 6. So 1.6 and 1.7. So the smallest markings are in between 1.6 and 1.7. Right?
Yes.
So smallest markings are in between 1.6 and 1.7. There are no smaller markings, so I can only estimate 1 digit past. So I know this is 1.6 something. 1.6 something. Now, is this closer to the 1.7 or is it closer to the 1.6?
1.7.
6.
Closer to the 1.7, right? A little bit further over to this side. Just a little bit past though, right? So what would you say this is?
1.66.
1.67.
You say 1.66, you say 1.67? Anybody else?
1.65.
1.67? Yeah, I would say either one of those are fine. 1.66 or 1.67 are both reasonable estimates. So I would say probably 1.67, I'd lean more towards that, but 1.66 actually may be more accurate. We don't know. It's estimated. So we're going to get slightly different answers, but that's how measurement works. And if we measure multiple times, usually that average will give us close to what the actual value is. Does that make sense?
But you know, Mike, but how do you know in the test that you are looking for tens and hundreds?
You
Because
look at what the
if you
smallest
have look, if you have a multiple choice, if one of the answer is 1.7, for example, 1.6, and one of the answer is 1.67, how do I know that which multiple choice I have to pick?
That's where you have to look at the actual measuring instrument. What are the smallest markings? The tenths place, right?
Yes.
If the smallest markings are in the tenths place, you need to go to the hundredths place. If the smallest markings are in the ones place, you need to go to the tenths place. If the smallest markings are in the hundredths place, you need to go to the thousandths place. You always have to go 1 digit past the smallest markings.
Yeah, that's a tricky question. If you have multiple choice, then you have to figure out that you have to pick 1.6 or you have to pick 1.67.
Well, if you were given a question, if you were given a question like that, you'd be shown a picture of the image that you're measuring. And so it wouldn't actually be that difficult of a question. It's actually a pretty easy question, because all you have to do is look at the smallest markings. What is the value of the smallest markings? Estimate 1 digit past. All right, so let's take a look at this. Go ahead and figure out what you think the length of this is.
This one is
We have a wooden stick. Write down the measurement here to the correct number of significant figures. All right, what do you get?
450,
For what?
4.5.
4.5?
4.5.
4.55?
4.55.
4.55? 4.55? Yes, so the smallest marking is in the tenth of a centimeter, and it's about halfway between. 4.5, it's between 4.5 and 4.6, so it's 4.5 something. So 4.55. Very good. Now, I would say it's actually a little bit past, so 4.56, but 4.55 is perfectly reasonable.
In this case, we choose option B, right?
I'm sorry?
In that case, we choose option B, right?
Yeah, you would choose, yeah, exactly. If you were given those choices, you'd be able to see, oh, I have to estimate between the smallest markings. All right, so now you'll see that I have 8 stations set up around the room, each measuring a different thing, okay? I have volume, temperature, length. For the tissue box, I want you to measure the height of the tissue box. For station number 5, I want you to measure the height of the table. Okay? So measure the height of the table, the height of the tissue box, and then measure the volumes and temperatures of everything else. Go ahead and you can either work with somebody else or you can work independently. But I noticed that there's 9 blanks, but you'll only need 8. So, this is our first measurement, station 1. Then we have station 2, our second measurement.
We'll be measuring inches or centimeters.
Centimeters. Excuse me. Skip ahead to station 4. We are measuring.
Mike, what is the unit for this? I should put millimeters or centimeters?
For the volume, look at the instrument. It'll tell you.
Milliliters. Okay. You don't have number 7?
There was one at 7.
There's 7.
Okay. Then. The height of the tissue box. Sorry. The height in centimeters of the table. Oops, I have the upside down, upside down. It's kind of difficult when it's shaky like that. There was something at 7. I'll have to check it out. Not sure. So, we look at the volume measurement here. At eye level. There we go. Sorry. Measure the
This beakers or you need this? This one? You need beakers or temperature?
Okay.
Mine.
And then we look at the copy. Let's zoom it in a little bit. Okay.